Well, good morning, kids. What we're going to do y'all go shut those doors so my Charmin accent doesn't echo throughout the libraries. I'm going to briefly talk about some of the mechanics of the assignment for optimizing the MPS, the Master Production Schedule. And then we're going to take what we've learned about optimization in our spreadsheets, and we're going to build a model for transportation, for minimizing transportation cost. What we've really been building up to all this time with optimization. Okay. So your assignment is here. I think everything you need is right in this module called Optimize MPS Assignment. Testing. Yeah. This is where you'll upload it. You'll upload both a Word document and a spreadsheet. It's due midnight on April 19th. And this is the actual assignment. This is where you'll provide most of your answers. And so you're going to want to open this and save it under a name, under your name. And you're going to see that what you'll do is you're building a model very similar to the models that we've been building. You got two things in it. And what you have to do, there's two things you have to do for this assignment. One, you've got to put the equations for the objective functions and the constraints. So whenever we've been doing a model, we've always been on the overhead and on the worksheets, we've been saying that this is the objective function, these are the constraints, you know, the summation and the AGEC, that kind of thing. And what's going to be a little different about you, is going to be a bit time consuming for you, is you need to do it in equation editor. And that's when you just go to Insert, Equation, and you use all that stuff. And there was one time in class when I had to use that because this wasn't working. And so it's kind of pretty, you play with it a little bit, you can understand how to do it. There are tutorials on it, of course. I find that most people can just play around with it enough to get it figured out. And I want you to do this in equation editor. One, so that the equations are exact and I know how to grade it. If y'all do it by hand, sometimes it'll be a bit jumbled and it'll be hard for me to tell like maybe exactly what you're summing over. You may leave some things out. And another reason is by making you do this in the equation editor, it's going to make you be more deliberate about what you're doing and make you think harder about what those equations look like. And so I think you'll learn it better. And so you'll have to put the objective function there, and then you'll list all the constraints there. And then you're going to build the model in Excel. And this is a bit different in that what you have to do, and I'm following basically the directions here, you've got to get this spreadsheet. And this is a macro-enabled spreadsheet. So some of you, your spreadsheets may not want you to be able to open macro-enabled spreadsheets. If it doesn't, just Google how to do it. It'll tell you something like go to Preferences, Privacy Settings, Enable Opening of macro-enabled workbooks. All right, and so I made this on my computer. We'll see. This will be kind of an experiment. See how well it works here. So the first thing you're going to do is you're going to come in and you're going to type your full name here. Then you're going to resave the file as your full name, and then you're going to come over here. Well, before you resave it, you click to begin. Okay, so this is saying macros may be disabled. And so we got to figure out how to undisable it. So maybe I'll go Options. Maybe privacy settings. No. Okay, so I just Googled how to do it. File tab, options, I think that's what I was doing, yeah. Trust Center, okay, Trust Center. Trust Center settings. Macro settings. Enable all macros. And you can just do this just with this spreadsheet. Okay, enable content. Okay, so there I got it working. You know, every different versions of spreadsheets may be different, but you can figure it out just like I did. Google will tell you how to do it. And once you click to begin and it says now it may begin, then you can start building your model. And here's the important thing. What this macro is doing is I want you to build your model from scratch inside your spreadsheet. I don't want you copying and pasting someone else's stuff. I don't want you copying and pasting even your spreadsheets that we've been doing in class. I want you to start completely over and build it from scratch. That way you'll learn it better and you'll remember it better if you do it like that. And so the important thing is, the only thing you need to worry about is just never ever copy and paste something from another spreadsheet or any other application or app. You can copy and paste in here, that's fine. You know, if you come in here and you do 2 and you paste again, that's perfectly fine because it's within that one spreadsheet. So copying and pasting within this one sheet after you've clicked the macro and said again is perfectly fine. It will let you, now the macro is not going to prohibit you from copying and pasting from another spreadsheet or another application, but what it's going to do, it's going to make a output file that's going to tell me if that happens. And if I go through there and there was even one instance of that, I'm not going to accept your work. You're going to have to start over. Does that make sense? Okay. You can still build it exactly like, you know, your model's still going to look very, very similar to the models we built in class. Like you take that last model, your model, you can build it to basically look identical to that, except there's going to be one more set of constraints on there. You just have to build it from scratch, that's all.
So it's going to look almost identical, you just build it from scratch?
Yeah, okay. That's right.
That's not terrible.
No. And, you know, it doesn't have to look exactly identical, but you'll probably want it to be as close as possible because that makes it easier for me to grade it and give partial credit. So what I'm going to do, if, you know, you put on the Word document, if you put the right answer, then I'm going to go to your spreadsheet and then I'm going to run your spreadsheet and make sure it actually gives you that right answer. And if you have the right answer, then I'm just going to scan things and if it looks okay, you get full credit. If you don't have the right answer, then I'm going to go into your spreadsheet and figure out what you did wrong and award partial credit accordingly. And so, you know, if you don't build the model like we've been building it in class, then it's harder for me to do that partial credit. And then you'll upload both the Word document and the Excel spreadsheet. Any other questions? Okay. Imagine this for a second. So let's think of a big business like Amazon or Walmart, even things like, you know, Atwoods or something like that. We're talking a business that deals with lots of supplies. And so maybe this is just a business that takes things in packages and sells them. They're not even really producing anything. And maybe this is like a nationwide store. And so they have lots of different acquisition places. So maybe like in each state, they've got a place where they initially get these goods to distribute. Maybe we're talking about vegetables. So every state has this center where they get the vegetables that they're going to then distribute to a lot of different places. Maybe we're talking, most of our fruits and vegetables come from California. So maybe we're starting off with like 4 different supply sites in California that's taking fruits and vegetables from different regions. And then their job is to send all those fruits and vegetables to half of the United States and maybe even beyond. And then what they've got to do, they say, okay, maybe there's one part of California is where a bunch of lettuce comes from, another part's where a bunch of almonds comes from, another part is where a bunch of strawberries come from, up in Washington is where all our apples come from, blah, blah, blah. It's lots of different supply sites. And then we have distribution centers. So these supply trucks are taking all these food items to specific distribution centers. Maybe there's 2 in the United States, maybe there's 5. And there they unload all the different things, and then they say, okay, this one store needs this much asparagus, this much lettuce, this much strawberries, this much apples. And so the distribution center then has to say, okay, we need to put these in, the right things in a package and send it to the Sprout store in Stillwater. And this can become something of a monster problem to solve because there's not just one place, one supply site where the lettuce can come from. It could be multiple sites in California, multiple sites in Oakland. There's people in Oklahoma who raise lettuce sometimes. So there's lots of different places we can take the lettuce from. There's more than one distribution center we can take the lettuce to. And then all that lettuce that's in one distribution center, there's maybe 900 different stores it can be shipped to. And so those are a lot of decisions to make. We know how much of each vegetable we have at each supply site. We know where our distribution centers are, and we know where our stores are and how much of each product needs to be at each store. And what we want to do is give each store what it needs in a way that minimizes transportation costs. And so we have to figure out, so this store needs so much of this stuff, which distribution center did it come from? Which supply site does that distribution center get its stuff from? And for small businesses, this might be a simple problem, but you can imagine for most grocery stores, this can be an enormously difficult problem. Too big of a problem for anyone or a group of individuals' minds to solve it in their head or even know all the parameters, know all the decisions that have to be made. What the person can do is build some kind of model where they understand the concepts and in general the decisions that must be made, but let the computer do all the storage of data, let the computer do all the number crunching. So one thing we're seeing a lot in supply chain management is that, as with most occupations now, it's a partnership between a human and a computer. The human doing what they do best, conceptual analysis, forming problems, letting the computer do what it does best, remember things, crunch numbers. And so we're going to learn how to build these models. And as you can imagine, these models can be really useful for a number of things. For instance, maybe let's suppose the Sprout store is considering, as it's expanding maybe in the north central plains, they're thinking maybe, do we need another distribution center? Will that save us money? That can be kind of a hard problem to answer, but if you have one of these optimization models and you hypothetically say, what if we have a distribution center here? Let's resolve our model. Now what are our total costs? We can see how much money it would save us. How much money a new distribution system will save us in terms of transportation costs, compare that to the cost of building a distribution center to say, should we build a new distribution center and where should that distribution center be? And the more you think about the difficulty of these problems, the more you're probably going to come to a conclusion that they're almost impossible to really answer well without some kind of transportation model behind you supporting it. And so we're going to start with we're not going to do really complex models in here, but we're going to start with some simple models, see how they're built, add some refinements, and so on. So the first one we're going to build, we're going to do it together. I'm going to be calling on you for things. If you don't know the answer, that's okay. And I'm not going to have slides. I'm going to be drawing the model, and I want you to draw it with me. So I want you to take notes on this. And I want you to draw it with me because as you draw it, it'll make you understand the problem better. And if someone needs some paper, let me know. And what we're going to start with is just a really simple thing where we have 2 supply sites and 3 stores. So I don't think, no, we're not even, we may break out the computers a little later, but we may not. All right. Does anybody need some paper? Okay. Now I'm going to go it may even seem a bit ridiculously slow building this simple model, making sure you understand it because we need to know the equations behind it, and we're only going to be dealing with refinements of this model. So just like you know that the MPS models we've been building, we started with something simple and it was just the same thing, we added sophistication to it. Same thing here, so I want you to understand the model well. All right, so what I'm going to do, I'm going to have this big sheet here, and I'm going to cover this whole sheet. I'm going to have plants over here, and I'm going to have delivery sites over here, and I'm going to draw lines between them. So I'm going to call, there are 2 places where we can get our vegetables from. And I'm just going to call them supply sites. So we're going to have supply site 1 and supply site 2. And we're going to say this is a transportation model for one good. And we're going to say supply site 1 has 100 units. That's how much it has. Supply site 2 has 125 units. And those 2 supply sites we're going to say are serving 3 different stores. So we're going to say over here, we're going to say, and instead of stores, we're just going to say region. So we're going to say over here we have region 1, region 2, and region 3. And that does spell region, even though that is an R. That's a G in the South Carolina language. Region 1 needs 25 units. Region 2 needs 95 units. Region 3 needs 80 units. Eventually, we're gonna connect these things, but eventually we want to take this model and represent it in mathematical form using variables. So you remember, how did we denote in the MPS model? We're saying how much to produce each month. We said production in any one month was denoted by XI. So X was production. And that was a decision variable. We don't have our decision variables yet, but also remember that we said when we made our production decision that in certain months we had to meet demand. There was a demand in certain months. Well, we have demand over here. And in that previous model, we denoted demand in each month by DI, where I subscript denoted month. Here, since this is demand, the demand here is 25 units, demand here is 95 units, demand here is 80 units, we can also denote that as DI. So like D1, D2, D3, I here refers to region instead of month. And so I'm going to call, this needs 25 units, that's D1. Needs 95 units, that's D subscript 2. Region 3 needs 80 units. We denote that by demand subscript 3. When we build our model, we almost never put in when we describe our model conceptually, we almost never put in exact numbers because this is a conceptual model. We're describing it, what it looks like, and we may want to go into the model later and say, like, what if demand here changes from 80 units to 90 units? And so instead of saying 25, 95, 80, we say conceptually D1, D2, D3. Now, as you can imagine, those numbers are going to form part of our constraints. Those are constraints there because we know whatever our solution is, we need to meet demand. That region 1 has to be provided at least 25 units. We're going to have another set of constraints over here that supply site 1 only has 100 units. So no matter what our decision is, we can't take more than 100 units from supply site 1. So that's going to be our constraints as well. And we're going to give those a variable name. What do you think would be a good name? So for demand, it was D subscript I. For supply site, what do you think we should call it? Half of you are thinking it right now, you just don't want to say it. Justin, any ideas? There you go. So the supply here is S1, supply site 1, S1, supply site 2, oh, I'm sorry. That's supposed to be 2, y'all saw that, you just didn't want to embarrass me. I appreciate that. You were helping me, you wanted me to catch the error because that's the best way for me to learn, right? I appreciate that. All right, S1, S2. Now ultimately, what's going to be the main driver of our decision of how much of these units goes to region 1, region 2, and region 3? What are we minimizing? Yep, we're minimizing transportation costs, so we need information on how much it costs to transport goods from supply site 1 to region 1, region 2, region 3, how much it costs to take stuff from supply site 2 to region 1, region 2, region 3. And so I'm going from supply site 1 I'm going to connect them like this. So what that means is it costs $250 to transport one unit from supply site 1 to region 1. It's $325 to take it from supply site 1 to region 2. $445 to take it from supply site 1 to region 3. When connecting supply site 2 to region 1, 2, and 3, I'm going to draw similar arrows, but I'm going to make them a broken arrow to help us better distinguish them. So I'm going to do this. And the cost of taking a unit from supply site 2 to region 1 is $275. From supply site 2 to region 2 is $260. From supply site 2 to region 3 is $460. These numbers, 460, 260, 445, 325, 250, 275, these are all per unit cost. Remember, in our conceptual model, we don't want numbers, we want variables. So we want to place 250 with some kind of variable for per unit cost. What would be a good letter to use? C, there you go. But the subscript is going to be a little different here. So if this number 250, this we're talking about going from supply site 1 to region 1. We've got one subscript here, so supply site 1 is supply site 2. There's 3 different regions, region 1, region 2, region 3. So whereas in the production, in the MPS optimization we did, we had C subscript I because there was a per unit cost per month. Here, it's going to be like CIJ, where I is the supply site and J is the region. But maybe instead of IJ, maybe we should use CSR. So the cost of going CSR from supply site S to region R. So this 250, this is the cost, per unit cost of going supply site 1 to region 1. C11, going from 1 to 1. Supply site 1 to region 1. This 325 are going from 1 to 2. So it's C1, 2. Going from supply site 1 to region 3. C1, 3. And rest assured, after we're done putting all these C's, we're not going to be adding more to this graph. I know it's getting fairly jumbled. This 275, that's from going from supply site 2 to region 1. So that's C21. 260 from going supply site 2 to region 2. C22. Supply site 2 to region 3. C23. And there's our model. That's the visualization of it. That's our concept of it. When you look at that, that probably makes perfect sense to you, but you can't give that map to a computer. You have to give the spreadsheet equations. You have to give Microsoft Excel solver equations. And so now we need to take all of this mess and put it in the form of equations. We're going to have CI, CSRs, and so on. So what we're going to do now is we're going to take this conceptual model here and we're going to make a list of our variables. And so far we don't have any decision variables because there's no decisions here. This is just the constraints and the cost. Okay. Decision variables. What are we trying to decide here? Give an example of something. What are we trying to decide? Say it in words. Somebody brave who's willing to speak.
Minimize costs.
Yeah, we're trying to minimize costs by choosing what? What's that?
Which supply side that we're
Yeah, which supply site we're getting from and then what we do with it, right? Yeah. How many units go from what supply site to what region? Right? And so we need some kind of variable for that, and usually the variable of default for decision variables is going to be X. So we have X. And remember before, with optimizing MPS, our decision variables was XI, how much to produce each month. But now we have more than one thing to consider besides month. We have supply site and we have region. So instead of XI, we're going to have XIJ. And that's going to be number of units shipped from supply site I to region J. And the use of I and J is arbitrary. It's just conventional in forming these problems that people like to sum over I's first, then they like to sum over J's first, then next probably comes K's and things like that. When we optimize MPS, I went from 1, 2, 3, 4, 5 because we went March, April, May, June, July. Here, I is going to go from 1 to what? 2. There's 2 supply sites. It's important we know that because when we sum, we're going to have summations, and here we're going to have double summations. We need to say sum I from 1 to 2. How many J's are there going to be? J is going to go from 1 to what? There you go, 3. And I think those are all our decision variables. I mean, all we need to know is how much goes from one supply site to what region. So, how many decision variables are there? How many XIJs are there?
Like combinations of?
Yeah. Yeah, yeah. To make sure you understand. So what we're choosing, the XIJs can be X11, X12, X13. So supply site 1 to region 1, supply site 1 to region 2, supply site 1 to region 3. We could go supply site 2 to region 1, supply site 2 to region 2, supply site 2 to region 3. So when we make that spreadsheet and we have that one row of decision variables, there's going to be these 6 variables there. Under our variables, we first had decision variables. I'm going to call that A because now I'm going to have a B. And these models, you either have decision variables or you have parameters. So we're going from A, decision variables, to B, parameters. Parameters or coefficients. Remember, parameters or coefficients refer to numbers that's just going to be given to us. And so numbers given to us, 1 is the supply at each supply site. And I don't want to, when I list those parameters, I don't want to say S1 and then S2, because sometimes we might have a model where we have 100 different supply sites. That's where this notation, where these indices, these subscripts come in handy. So one parameter is going to be SI number of units available at supply site I. How are we going to denote our variable for the demand needs at each region? Any ideas, Gavin? Yeah, so we could go D1, D2, D3, but I don't want to list all the Ds because sometimes we may have 1,000 different demand sites. So instead of D1, D2, D3, I want to say D. Nope, I don't. I's been used. J, exactly. All right, so we got supply, we got the demand. The other number given to us is the per unit cost. C, what my indices is going to be there? IJ. I'm going to start putting formulas to this for a minute, but let me stop here and talk a little bit about how often this kind of stuff is used. So you're seeing this being used in business decisions like production decisions and transportation decisions, but this kind of model where you're optimizing, minimizing, or maximizing something to constraints is used in a ridiculously number of different fields and contexts. So it's kind of obvious how it's used here, but I'll give you another example. I once interviewed a robotics engineer, and what he's doing, he was building robots to go out and scan an apple field and determine how many ripe apples were on each tree, to know what production was like throughout the field. And for most of what his job is, it's putting algorithms into a machine. And so conceptual models, kind of like this, into a machine, and then the machine runs it. So for him, instead of minimizing or maximizing something, it was like accuracy. This machine would go out and it would, using its visual abilities, count the number of apples, ripe apples in a tree, and then people would go out and count them by hand and then see how close did this robot get to getting the true number of ripe apples. And so there they were minimizing the distance between predictions and actual observations. And that machine has to also work under certain constraints. It has to move a certain way, a lot of other things to it. Visual representation. So what do you call it when they take pictures of you, and like the police when they...
Mugshot?
No, yeah, but when they use computers to say who this is.
Facial recognition.
Yeah, facial recognition. They're doing things like this. In every form of engineering they're using models like this. You almost will not go into any graduate program that's quantitative in nature, whether it be economics, ag economics. So our grad students take a whole course in math programming. That's this on steroids. Industrial engineering, chemical engineering, even certain fields like sometimes like human resource management finds ways of using this thing. So this is a very general tool that has just a ton of different applications. Okay, so we've got our variables. We know what our decision variables are, and we know what our parameters are. Now, we just need to represent the objective function and the constraints in mathematical form, and we're done, and we'll stop there. So the better you help me do this, the closer you get to your lunch. I know Rachel and Ethan are already through with their breakfast. It's lunchtime for them. We need to get them out there. Okay. Objective function. Are we minimizing or maximizing something? Come on, you know this. Minimizing. We're minimizing transportation costs. We have these decision variables X, I, J, and we're minimizing how much it costs to ship these things. Now let me show you the objective function in a way that would make sense to you before we apply summations to it. So this probably makes sense to you. X11 is the number of units we're taking from supply site 1 to region 1. C11 is the cost of moving a unit from supply site 1 to region 1. So if we multiply those two variables together, that's the cost of moving all the stuff we took from supply site 1 to region 1. That's the cost of moving all that stuff. This right here, let's take this one, C21, X21. X21 is the number of units we're moving from supply site 2 to region 1. C21 is the cost of taking one unit from supply site 2 to region 1. So multiply those two units together. That's the cost of all the stuff we move from supply site 2 to region 1. And I already said we had 6 decision variables. Each of them have a cost, so we have 6 terms there. And you can imagine in that spreadsheet, you have that one row of 6 decision variables, and right under it, you have the CIJs, the per unit cost for each one. And that objective function you're minimizing is the sum product of that one row and the other row. But of course, you know, we can have 20 different supply sites, we can have 50 different regions. So we don't want to write it out like this, we want to condense it using the summation term. And we're summing 2 things here. When we optimize MPS, we just summed over months. You know, the cost of producing in March, plus the cost of producing in April, plus the cost of producing in May, plus the cost of producing in June, plus the cost of producing in July. But now we're summing over I's and J's, supply sites and regions. It's not just I, it's I and J, and so we're going to have 2 summations there. But I know maybe some of you have never seen double summations or something, so I'm going to get to the double summation slower. One way I can rewrite this is to say this. These 3 terms, I collapsed it down to this. Because look at this term. The first subscript is always 1. 1, 1, 1, 1, 1, 1. So I have C1, X1. And then in these 3 terms, J is going from 1 to 2 to 3. So sum J from 1 to 2 to 3. Likewise here, I'm collapsing these 3 terms to this one summation formula because the first index is always 2, 2, 2. And then there's 3 terms we're summing where J goes from 1 to 2 to 3. J equals 1 to 3, J, J. And now I can collapse those 2 summation terms into a double summation term. Because notice what happened here. Here, the i's are 1s. Here, the i's are 2s. So I'm doing a summation where first I equals 1 and then I equals 2. So I'm summing from I is 1 to 2. Then I'm summing from J is 1 to 3. Going from C, I, J, X, I, J. So we're minimizing this objective function by choosing the xij's. And we're only really going to have 2 sets of constraints. Everybody cool with this? All right. In words, what is one set of constraints we need to consider? You know it. Lance? Can you kick them, Rachel? I don't think you heard me. What's one thing constraining? Yeah, we got demand and we have what? And supply. You knew that, right, Lance? You're just shy. All right. Have you never asked a girl out, Lance? I mean, that has to be worse than this. Or is it all electronic? You just swipe left or right and you just... See, this is what happens when electronics does the dating for you. You can't even speak up. And see, I spent my whole life being rejected by girls, and that's why I can get in front of a crowd, and it just doesn't bother me at all if I'm wrong. All right. So, Lance, your assignment is today... No, I'm not going to do that. Okay. All right, so... Not even thinking in summations. How do we represent... Okay, this is saying right here, supply site 1, you can't get more than 100 units. And we need to think about how to get that in mathematical terms. So meaning, all the stuff we take from supply site 1, whether it goes from region 1 to region 2 to region 3, cannot exceed 100. So when we're thinking left-hand side and right-hand side, we want decision variables on left-hand side, parameters on right-hand side. So we're thinking constraints. And we're going to have a left-hand side, which should always refer to decision variables. Right-hand side, which should always refer to parameters. And in the middle, there's going to be a greater than or equal than, or less than or equal than. All right. So when we're thinking of supply constraints, and we say we can't take more stuff from supply site 1 than 100 units or however much there, are we thinking equals, greater than, or less than? What comes to mind? We're saying you can't take more than 100 units. You can't take more than SI. You can't take more is the same as less than or equal to. You knew that, right, Courtney? Yeah. Y'all are ridiculous people. You really are. Less than or equal to. All right. We know if we were just dealing with supply site 1, we could, in the spreadsheet, we're going to put 200, we'd put 100 units. Must be less than or equal to 100 units. But we want one equation for all our supply side constraints. And so instead of 100 units or S1, we're going to put SI. Okay. But now we need something on the left. So we need to say stuff that comes from SI, from supply site 1, can't exceed SI. Okay. What is the variable that says how many units come from supply site 1 to region 1? X is our decision variable. Number of units go from supply site 1 to region 1. X. Trevor? Yeah, if we're going 1 to 1, yeah, you're thinking right. Yeah, IJ, you're thinking right. If we're going 1 to 1, that's X, 1, 1. If we're going I to J, it's IJ. And so what we're saying is like, So we've said SI right here. So it's like we're holding the arbitrary I constant. I is going to stay there because we're going to say this has to hold true for all I. And so we know our X's are always going to have I's. And so the other thing, and we know there's, think of it this way. We know what we're saying is that x11 plus, for region 1, for supply site 1, x11 plus x12 plus x13 has to be less than or equal to S1. And so there, the 1 was held constant and the J's went from 1 to 3. So if we have SI over here, and I know this is hard to get at first, but with practice, it'll become second nature too. What we're really saying is that xi1 plus xi2 plus xi3 has to be less than Si. So if I is 1, we're talking about supply site 1, x11 plus x12 plus x13 has to be less than or equal to S1 of 100. Stuff that comes from supply site 1 to region 1 plus stuff comes supply site 1 to region 2 plus stuff comes supply site region 1 to region 3 has to be less than the amount of stuff we have at supply site 1. If I is 2, it's x21 plus x22 plus x23 is less than or equal to S2. But whenever we can, we don't want an equation like this. We want to collapse it to a summation because, again, we may have 100 regions sometimes. So instead of this, I'm going to write it as what am I summing over? I's or J's? J's, that's right. There's 1, 2, 3 terms, 3 J's. So J equals 1 to 3. The sum of Xij must be less than or equal to Si for all I. Which means in your spreadsheet there's going to be one line for it for region 1, one line for it for region 2. And again, I know dealing with these summations is a little difficult at first, but again, we'll practice it and it'll become second nature. Well, it won't be second nature, but you'll feel better than you will now. One more set of constraints. Okay, so if that's our supply constraint, we're going to need a demand constraint. And what our demand constraint is saying is that we need to make sure that we send enough units to each region to meet demand. And I know initially that would make you think equal. That's going to be your first impulse. But there's, for reasons it might be hard to see right now, in programming, you only use the equal sign if you have to. Whenever you can use a greater than or equal to or less than or equal to, that's the preferred way. So we need to make sure however much we send to region 1 is equal to or more than demand for region 1. However much we send to region 2 is more than or equal to needs for region 2. However much we send to region 3 is more than or equal to at needs for region 3. So there's 3 different constraints there, one for each region. So there's like 3 different lines, and so we're saying that has to be true for all regions. J here's regions, all J. So we know at the end, whatever equation we have, we're going to say all J. This constraint has to be true for all J's, all regions. We're saying however much we send there has to be equal to or greater than, so it's going to look like that. And then our demand for region J was just DJ. And imagine you kind of see what should be here. So if we take any region J, it can come from supply site 1, it can come from supply site 2. And we have to make sure that the amount that comes from supply site 1 plus the amount that comes from supply site 2 is greater than or equal to the demand there. So I'm going to write it first without the summation, then we'll put in the summation. So for any J, the amount that comes from region 1 is X1J. The amount that comes from region 2 is X2J. And you know, whenever we know there's a different constraint for each region has a different demand. So there's going to be an all J here. And whenever you have all J, you know there's going to be J's on both sides of the equation, and you're never going to be summing over J's because the summation gets rid of J's. The J's has to stay. Notice this is like Xij when I is 1. This is like Xij when I is 2. So another way of writing this is we're summing over all supply sites 1 to 2, Xij must be greater than or equal to Dj for all J's. And just to make sure we have it all, I'm going to rewrite them. Because we have everything we need now to actually build this model on a spreadsheet. Our problem is to minimize by choosing Xij's, the sum, I equals 1 to 2, sum, J equals 1 to 3, Cij times Xij. That's what we're minimizing. Subject to the amount that comes from any region must be less than or equal to supplies at that region. And the amount that's sent to any region must be greater than or equal to demand in that region. No, I can't get it all, but there's our objective function. There's our constraints. And the last thing is, remember, the key to making sure we get these equations right is, you know, I've got an error there. Anybody see the error? That should be I. When you have a supply constraint for each supply site, there's one for each site. I was the sites. So you're summing over J's. When you sum over J's, you get rid of the J's. So everything is I's denoting the site. When we're talking about region, you've got a constraint for each region. You know the J's are going to stay there, and you're going to sum over the I's because it gets rid of the I's, and everything left is J for each region. And then what we're going to do in next class is we're going to build that model in the spreadsheet. Bring your computers, you're going to build it. I'm going to go around and help you, and we'll just have a jolly good time. Have a great weekend. Yeah.